Okay, so we're going to look at Chapter 3, Representations of Data. And again, thank you to Dr. Frost for this great PowerPoint. I've merged a few of them because it's different spec than the UK one. So in this chapter, what we're going to look at is box plots. Now, this is in the GCSE, and stem and leaf diagrams are in the GCSE. But we don't have them in the IGCSE, so we are going to start from the beginning with them, okay? Box plots and stem and leaf diagrams. And then histograms. Histograms are in our IGCSE, and we do go into a lot of depth with histograms. We're only going to be looking at really something a little new here, okay? Nothing much. So, what we're going to do is, so this is just called data representation, okay? So nice and easy. Right then. So here we go, we're going to learn about stem and leaf diagrams. Now, I love a stem and leaf diagram. Haven't taught this for a few years, but they're really, really simple, okay? So, what we have to do when we have a look at a stem and leaf diagram is we have to make sure we're putting these in a diagram. That's what we're doing. And this is how a stem and leaf diagram looks. So, we always have to have a key, okay? With a lot of diagrams, we always have a key. Okay, and for this key, what I'm going to say is, for line 7 means 4.7. This will become more apparent in a minute. Okay, so we have a key. We always have to write key. Then what I'm going to do is I can see, if I have a look at my data here, I think my lowest number is 1.4. Okay. Highest number, 5 point something. Okay, so immediately I know then we're going to have 1, 2, 3, 4, 5. Now, my lowest number, 1.4. So, what I'm going to write is 1.4. Okay? Because I know that 1 and that line, 4 means 1.4. Okay, now let's move on to the 2s. So what's my lowest 2? I have 2.2, 2.4, 2.1, 2.5. Okay, so 2.1 is my lowest. So what I do is 2.1. Then my second lowest was 2.2. So what I now do is I'm just going to write a 2 next to where it says 1. Okay, so this is 2.1, 2.2. Okay. Then, what do I have? After 2.2, I have 2.4 and 2.5. So then I have 4 and 5. So I know this represents 1, 2, 3, 4, 5 data values. This represents 5 data values. I have 1.4, I have 2.1, I have 2.2, I have 2.4, and I have 2.5. Okay, and we have to write this in order. We're writing this in smallest to largest for each point, for example. We could do this, and instead of it being 1 point, this one could stand for 100 maybe. Like this could be 104, couldn't it? And then we would write that here, okay? It really just depends on what's going on. So if we carried on, let's start on the 3. Okay, so let's look at the 3. So the smallest 3. Now sometimes it does help to put this in order, okay? But it's entirely up to you. So the smallest 3, I think, is 3.2. So I'm going to have 3.2, and I am going to cross that off, okay? There's nothing wrong with good old-fashioned crossing it off to make sure you don't miss anything out. If you're confident, please go ahead and keep going with this. Then what do I have after this? I think it's 3.5. I can't see a 3 point. So we're going to have 3.5. 3.66. That's 2 6s. 3 6s. Okay, 3 6s, 3.7 and 3.7, 2 7s, 3.8 and 3.8, and 2 8s. Perfect. Okay, and then for the 4s, my lowest one is 4.0, 4.1. I think I've only got one of them. Then I've got 4.2, 4.2, 4.4, 4.5, 4.6, 7777, 1, 2, 3, 4, and 8. Okay, then for my 5s, I've got 5.0, 5.1, 5.1, and 5.2. Okay, so this is a completed stem and leaf diagram. We've got our key and we've also got all of our data sets in. Okay, now what we're going to look at is we're going to look at finding the mode, the lower quartile, the upper quartile, and the median. Okay, so this is easily done from this set of data. Now, we have to, first of all, the mode is the most common number. Okay, so if I look at this data set, the most common number, I can see there's 4 7s in this row. I don't think there's 4 of any other number, so 4.7 is the mode, because that's the most common number. It's the number that appears the most time. I then want to find my median. Okay, so my median is going to be my middle number. Now, if you wanted, you can go back to old-fashioned. So, start with the smallest, 4, and the biggest, 2. Yeah, because 5.2 is the biggest number. Then, the smallest, 2.1, the second biggest, 5.1. So, we could cross it off this way, and we could keep going like this, okay, until we reach the middle. Okay, that's one way we could do it. And if you would like to do that to get a bit comfortable, that's fine, because I know you haven't seen stem and leaf before. The other way we could do it, we know we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We have 30 sets of data. So where's our median position going to be? 15. It's going to be in between 15 and 16, isn't it? Okay, because it's an even number, 30. So if I was to count this, I know I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what's in the middle? These are my 15th and 16th values. Okay, 4.0 and 4.1. So my 15th value, 4.0. My 16th value, 4.1. What's in the middle of that? 4.05, absolutely. Okay, so again, you can cross out whatever you would like to do. Then we have our lower quartile. Okay, if I did 30 and I divided it by 4, what's my answer? 7.5. So which term am I actually looking for? So if I have a look, 1, 2, 3, 4, 5, 6, 7. Okay, but it's given me 7.5, so I round it up. So I want the 8th. So I do want the 8th term, which in this case is 3.6. Okay. Then to find my upper quartile, I'm going to do 30 multiplied by 3/4, which we know is 22.5. We're going to round that up. That's going to give us our 23rd term. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, which gives us 4.7. Okay, now again, remember what I said in the last chapter, okay? Remember there's 2 ways to do this. If you have a set of data, okay, to find the median position, you do n plus 1 divided by 2, okay? If this is only for a set of data, this isn't grouped data, this is a set. Here we have a list, don't we, like a list of data. If you want to find the lower quartile, you're going to do n plus 1 divided by 4. If you want to find the upper quartile, you're going to do 3 lots of n plus 1 divided by 4. This will give you the position. Okay, the other way you can do it, and this is how Dr. Frost explains it sometimes, is, so here we know the median, half of 30 is 15, so we know it's in between 15 and 16, okay? But if you just did 30 plus 1, divided by 2, you get 15.5, so you know that. Then when we're finding the lower quartile here, it gave us 7.5. We actually need to round up to the 8th. But if you're not sure as to why we do that, if you put it into this formula, 30 plus 1 divided by 4, what would you get? Definitely wouldn't get 8. But it would lead you to round it up more. Okay? So you've got to remember, the other thing you could do is in between 1 and 16, what is in the middle? Okay? Between 1 and 15, because essentially you're finding the median of this data then, not including this, okay? Okay, so here then the other type of stem and leaf is called a back-to-back stem and leaf. This is really simple, okay? This is basically where in the middle you would have our key, and then you'd have, for example, girls on the left and boys on the right. So if you were to do a key, okay, if you have a look here, I've got 55 girls for my first one. So let's just do 5, 5, 4, okay? This would mean 55 girls and 54 boys. Okay, because girls is the left-hand side. The middle column is actually in here. In this case would be our tens. Okay, so we look for the smallest number in our list. I think it's 40. So I know that 4 is going to be my smallest number. You look for the highest number in the list. 90. So I know I'm going to have 4, 5, 6, 7, 8, 9. Now you can start on the girls first and then do the boys after, that's fine. So if you think, for the girls, we do have 40, so I know that's 40. So we're actually working, this is like how you read Arabic, isn't it? 4 and then you have 0. Yeah, so imagine one side, the girls' side is reading in Arabic and the boys' side is reading in English. Or left to right, is that right? Yeah. Okay, so then, we'd fill this all in. So we're going to have 50 what? 4? 55, 58. So 4, 5, 8. 60. 0. 4. 6. Okay. Then we're going to have 70. 2, 6, 8, 9. Then we're going to have 80, 0, 0, 0, 4, 5, 8. Then we're going to have 90, 0, 1, 2, 6. Oh. So you can see there, I've done it slightly faster, okay? Have I done that right? I think I've forgotten another 2. And an 8. Oh my. 2, 2, 6, 8. There we go. Okay, I think that one's all done now. Right. Boys. This looks a bit easier. Okay. 40, 6. 50, 0, 7, 9. 60, so we've got 0, 0, 4, 5. 70, 1, 2, 4, 5. I've just realised there's a 68, and a 7. So I'm going to have a 7, 8. And then 80 is 0 and 90 is 1. Okay, perfect. Completed and done. So it then says comment on the results. overall, what can we see by this stem and leaf diagram? Because it is also a bit of a diagram. It's you know, a representation of data. What can you see by this? There is more results by girls, but look at the spread of the data. Look at where the data is leaning towards. You think about the pulse rates of girls and boys. What would you say about this? Yeah, the girls, if you look at the data here, it's more leaning towards the 80s and 90s, whereas this data is more focused on the 60s, you know? So actually, the girls, from the data, the girls' pulse rate tends to be higher than the boys, doesn't it? So you'd write that. The girls' pulse rates tends to be higher than the boys. Okay, so that's nice and easy. This is stem and leaf diagrams. So box plots are in the GCSE spec. They're not in the IGCSE spec. These are really simple to plot. Okay? You need 1, 2, 3, 4, 5 sets of data. You need the minimum point, the maximum point, the lower quartile, the upper quartile, and the median. And this is how it looks. Very simple. Are we ready? So we're going to plot the median. 17 is roughly here. We're going to plot a line like this, because what we're actually going to make is a box. Okay? We're going to plot the upper quartile, 22, roughly here. We're going to plot the lower quartile, 15, roughly here. Okay, and then we draw a box. Now this box is made by the median, the lower quartile, the upper quartile. The maximum, 27, roughly here. We're going to draw a shorter line, and we're going to connect it like this. Okay? And then the minimum is 3, it's roughly here. And then we're going to draw it like this. Okay, so step 1, we just need to understand how to draw it. What's going to be really fascinating is in a minute, we are going to look at what this means, what the spread means, what each box represents. I'm really looking forward to this, because when we understand what's going on, this is my favourite part. Get some good, meaningful discussions going on. Okay, so I've highlighted, colour-coded it for everyone so that you can see. Being able to draw this is just step 1 easy. This is how we draw a box plot, okay? So, now we have 2 questions I really want you to think about. I want you to discuss, and I want you to come up with some crucial questions. Remember, we teach this at GCSE. We're now in A-level. Think about the types of questions and answers I'm looking for. Off you go, a few minutes. Absolutely. We know to find the interquartile range, we have the upper quartile minus the lower quartile. So the width of this box is going to give us the interquartile range, okay? So it is the width of the box. Okay, how is the range represented in this diagram? So we know that this part here is the interquartile range. And how is the range represented? Yeah, these 2 endpoints here, because we have our minimum and maximum points, okay? Perfect. So, I would like you to try your own box plot before we really get into some questions about what we can tell about the data. Off you go. Okay, so first of all, step 1, is the data in order? It clearly is. So I can write my minimum and my maximum. So my minimum is £5, my maximum is £20. That must definitely be a heavy cap. So, then what we need to do is find the median. Now, if I take a look at how much data I've got, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so £8 is the median. Oops. Then my lower quartile, okay, is the median of the left-hand side. So what I mean is by here, look. So here you'd have 1, 2, and then you'd have 3, 4. So our lower quartile is in between 6 and 7.5, which is in fact 6.75. Then our upper quartile between 9 and 20, 12, so it's in between 12 and 14, which is in fact 13. Okay, I now need to sketch this. So my minimum is 5, my maximum is 20, my medium is 8, my lower quartile is 6.75, and my upper quartile is 13. I'm going to draw my box. Okay. This is what my box plot should look like. Okay, so you've got another test your understanding. Now, this time, I wonder, I haven't taught you how to do this yet, but I wonder if you can figure this out. Okay, have a quick conversation, let me know. Okay, so if you think about the median, okay, if you think about the median point, the median point is right in the middle of the data, isn't it? Yeah? So, actually, when I look at this box plot, from the minimum to the lower quartile, this represents 25% of the data. From the lower quartile to the median, this represents 25% of the data. From the medium to the upper quartile, what does this represent? 25% of the data. And then finally, from my upper quartile to my maximum, this represents 25%. Now this is what we got to get used to. They all represent 25%, but they're not equal, and that's okay because the data is not equally distributed. Okay, that's fine. My upper it says there were 80 players in Colin's sample, so I know this is represented by 80. Okay, there's 80 altogether. And then it says work out the number of players who ran a distance of more than 5.6. So step 1, find out where 5.6 is. 5.6 is actually here, which is in fact my upper quartile. Okay, that's where 5.6 is. Who ran more than 5.6? Well, actually, it's my upper quartile to my maximum, which I know is 25% of the data. So what's 25% of 80? 20. So this is how, so well done those of you who got 20. So 25%, okay, of 80 is 20. And that's the number of people that ran more than 5.6 kilometres. Okay. So, comparing box plots. Now, when you compare box plots, you're going to get 2 marks. Okay? Essentially. You're going to get 1 mark for either comparing the interquartile range or the range. Okay, 1 mark for either of those, but not if you wrote both of those down, you're not going to get 2 marks. And then you get 1 mark for discussing the median. Okay? So you have to discuss the median, and then the other mark you can discuss the interquartile range or the range. So let's actually have a look at house prices of Croydon and Kingston. So here we go. If you're comparing the interquartile range, okay, what could we say about the interquartile range? Well, the interquartile range in Kingston is larger than Croydon. So we can say that. So interquartile range of house prices in Kingston is greater than Croydon. And you can see this is a full sentence. Okay? The range, so range of house prices in Kingston, okay, is greater than Croydon. Perfect. Okay, either or. Yep. And you can see here, like sometimes people put figures in. It really depends, you know, what's going on. You can put figures in. Then the median. Okay, so median. Oh, I've got my highlighter out. So median house prices in Kingston is greater than Croydon. Okay, nice and easy. Okay, because you are going to have some questions that say explain this. At least you know where these marks are coming from. Right then, so what we're going to have a look at quickly is these box plots, interpreting them. Have a look at these statements. Are they true or false? Okay, so interpreting box plots, we know that even though this right box is bigger than this left box, it does not represent more people because we know it represents 25%. So this is false. And then for the second one, the ages are more spread out above the median. Well, if I look at the median here is 10. From 10 to 28, okay, is above the median. And then here I have from 10 to about 3. So the ages are more spread out above the median, which is true. Okay, here we have it. What is an outlier? Does anybody know what an outlier is? An outlier is defined as an extreme value. Okay, it's an extreme value. So an extreme value. Okay, here's an extreme value. And there's a common definition. And an outlier is where 1.5 interquartile ranges beyond the lower and upper quartiles. Okay. So what this means is, we know our interquartile range is this part here, okay? And this part is roughly, I mean, I'm just guesstimating here, I'm going to say between 15 and 22, yeah? So this is about 15, this is about 22, okay? So this is 7 long. Yeah? Now, what is 1.5 lots of 7? Yeah, 1.5 times 7. 10.5, exactly. So, we then go from the lower quartile. Now, you can see here, this is a whole one, then this is half of this whole one. This is going to make 10.5, yeah? So, we have here 10.5. Okay? So 15 take away 10.5 is 15 take away 10.5. 4.5, thank you. So 4.5 is roughly here. Okay? Then on the other side, 7 plus 10.5, because that's 1.5 lots, is 17.5. Okay, what's 22 plus 17.5? 39.5. No. I've gone completely skew. What's 7 times 1.5? 10.5. Okay then, 22 plus 10.5? 32.5, which is, as we could say, roughly here. Oh. Okay, so an outlier is identified as a point that lies outside this value. As you can see here, our minimum actually lies outside this value. So we would say our minimum and maybe another data point could be outliers, okay? You will be told in the exam if the rule is different to 1.5 interquartile ranges. Okay? Right then, so here are two examples of types of outlier questions. Okay, so type number 1. What we have to do is, first step, the diameters of 11 different Roman coins are measured in centimetres. Determine the quartiles and hence any outliers. Okay, so first of all, what do I know? This is in order. Perfect, right? In order. Okay, so let's find the median. Okay, now remember, the lower quartile is quartile 1. The median, quartile 2. The upper quartile, quartile 3. Okay, so I'm just going to go good old-fashioned to 4.7. Okay, because it is a list of data, I can do this. Okay, 3 is my median. Okay, we don't actually need the median, but we're just doing it for fun, really, aren't we? Okay, then we're going to have 1, 2, 3, 4. 2.7 is our lower quartile. Okay, and then 3.1, 4.7, 3.2 is our upper quartile. Okay, so our interquartile range is found. Interquartile range is found by taking away our upper quartile, lower quartile from our upper quartile. So we get 3.2 minus 2.7, which is 0.5. Okay, so the lower bound outlier. So we know if we were to draw this, we got 0.5. Yep. So then, if we were to do below 1.5 times of 0.5. Thank you, 0.75. Because we're going to have another 0.5 and then a half of 0.5, which is 0.25. So we're going to have 0.75. And then again, moving up, okay, 0.75. This is a terrible drawing. But anyway, what we now have to do is, so our lower quartile, so how we work this out is this. Remember, this here is our lower quartile, quartile 1. This here is our upper quartile, quartile 3. Okay? Our lower quartile, take away 1.5 times the interquartile range, which we know is 0.75. Okay? What does this give me? Now, so I'm going to have 2.7 minus 0.75, which equals 1.95. Okay? Do we have any outliers which are lower than this? This is called a lower outlier. So this is our lower outlier boundary. Is any of our data lower than 1.95? No, so we don't have any outliers which would be on the left of the graph, essentially, yeah? Okay, and then my quartile 3, my quartile 3 plus 0.75. So this is going to be 3.2 plus 0.75, which is in fact 3.95. Okay, do I have any data values which is higher than 3.95? Actually, I do. Okay, 4.0 and 4.7. So therefore, 4.0 and 4.7 are outliers. Okay, perfect. Now, this is just a little example as to how this works. But do you really think you're going to get a question this easy? Absolutely not. Okay, so are we ready for an actual example? Okay, here we go. The lengths in centimetres of 12 giant African land snails. Has anyone ever seen a giant land snail from Africa? Yeah, they can get pretty big actually. Okay. Yeah, I had to look after one once. So, they're given below, and it says calculate the mean and standard deviation given that the sum of x is 252 and the sum of x squared equals 5468. Okay, do we remember standard deviation? Yes. Yeah? Yeah. The mean of the squares minus the square of the means. Yeah? something like this. So, here we go. So here it goes. We know to find the standard deviation. Standard deviation is the variance squared. Sorry, the variance is the standard deviation squared. We know that this is what? The mean of the squares. So the sum of x squared over n minus the square of the mean. The sum of x over n squared. Okay, you need to know this formula. Here it is. If you don't remember it, just remember me stood here. Okay, so then we know to find standard deviation, we need to square root all of this. Okay, so the sum of x squared, 5, 4, 6, 8. Who do we appreciate? Well done. So 5, 4, 6, 8 divided by 1, 2, 3, 4, 5. Oh, it tells us there's 12. Okay, always read the question. 12. We're going to minus that from the sum of x, which we know is 252, and divide that by 12 again. And then we're going to square it. Okay, I'm literally going to put that whole thing into my calculator. Okay? And magically it's going to pop up 3.83 rounded to 3 significant figures. Perfect. Okay, nice and simple. Now, it then says, an outlier is an observation which lies plus or minus 2 standard deviations from the mean. Identify any outliers in this data. So this is the case where they're telling you a new rule. Okay, this isn't the quartiles rule that we just did. This is a brand new rule. Let's read the rule. Plus or minus 2 standard deviations. We know the standard deviation is 3.83 from the mean. Okay, what is our mean? So I've got to work out the mean of the data, which we know is 252 over 12, which is 21. So let's just double check what it says. It lies plus or minus 2 standard deviations. Okay, this is 2 lots of. 2 standard deviations means this, doesn't it? So we need to do the mean, which is 21, plus 2 lots of the standard deviation, which we know is 3.83. This is going to give me 28.66. 28.66. Are there any numbers greater than 28.66? Outlier. Okay, and then to find the lower bound, we're going to do 21, because that's the mean, minus 2 lots of the standard deviation. 7.66. 13.34. Are there any data values which are less than 13.34? No. Okay, therefore, 32 is an outlier. Okay then. So, pretty simple really. Okay, it's that time of the lesson. Test your understanding. So here's the age of 15 Lib Dem MPs are given. Okay. If an outlier is considered to be 1.5 interquartile ranges below the lower quartile or above the quartile. Okay. Determine any outliers. Okay. Did anyone find the lower quartile? 27 is the lower quartile. Oops. And the upper quartile? 58, I'm assuming. Okay then, so quartile 1 is 27, quartile 3 is 58, and 1.5 in the interquartile range. So interquartile range, 58 minus 27, 31. Perfect. So what we're going to do then is, let's see. Let's have a look at our lower boundary. We know 1.5 times 31 is what? 46.5. So quartile 1 minus 46.5 is going to give us our lower boundary. I can immediately see that 27 minus 46.5 is going to give me a negative number. So 27 minus 46.5 equals negative 19.5. This is our lower bound. Do we have any data values that are less than 19.5? No. Sorry, negative 19.5. No, so it's okay. It's okay. Right, our upper bound, quartile 3 plus 46.5. So that's going to give me 58 plus 46.5, which is going to give me 104.5. Okay? Are there any data set values above this boundary? Absolutely. 105, outlier. Therefore, 105 is an outlier. Perfect. Okay. Right, the last one. If instead, an outlier is considered to be outside 2 standard deviations. Okay, 2 standard deviations means 2 multiplied our standard deviation. Within the mean, determine any outliers. Okay, so first of all, what do we need to know? We know the variance is calculated by the sum of x squared. Okay, so it's the sum of the means. No, the square of the means minus the mean squared. Okay, the mean squared, absolutely. Okay, and from what we actually need to work out the mean as well. So how many? 15. So 613 divided by 15. 40.8666, let's call it 40.9. Right then, and then we know to find our standard deviation, we're going to have our square root of 33,815 divided by 15 minus 40.9 dot dot dot. Okay, but we would squared, put that in his answer. It's going to give me 24.2 to 3 significant figures. Okay, please make sure you write down what you're rounding. So, what are our boundaries? So, the mean is 40. So, our lower boundary is calculated by doing the mean minus 2 lots of the standard deviation, which is 24.2. So, that means our lower bound is, in fact, negative 7.5. We do not have any outliers because we don't have any data sets lower than negative 7.5. And then our upper boundary is calculated by 40.9, our mean, plus 2 lots of our standard deviation, which is going to give me 89.3. Do we have any data values that are above 89.3? Yes, the same culprit, the 105-year-old. Therefore, 105 is an outlier. Perfect. Okay, so we've got this question, exam question. 14 marks. Okay, so here are the answers for that. Test your understanding. Pause it, have a look at what's going on. Okay, now sometimes it asks you to draw a box plot to represent the data above, okay, and we've also got to show our outliers in this. Now what they've done is they haven't told us all of the data, but they've told us the 2 smallest values, 0 and 3, and they've told us the 2 largest values, 21 and 27. So imagine we had our list of data. This is how it's going to look. 0, 3, we don't know the middle, 21, 27. Okay? That is what we know. Right? So, just in this example, this is what we've been given. So we need to draw a box plot to represent this data. Now, I'm going to draw the box plot and then we'll tidy it up. We're going to delete some things. So if you're copying this down, Just be a bit wary of what's going to happen, okay? I'm going to be rubbing out stuff. So, first of all, let's find out our interquartile range and see if we've got any outliers, okay? So our interquartile range, we know is quartile 3 minus quartile 1. This is what our interquartile range is, and this is 14 minus 8, which is 7. Okay? No, it's not. It's 6. Okay then, so 14 minus 8 is 6. Right, then what we're going to do is we know we're going to have our lower quartile, which is 8, minus 1.5 times of 6. 1.5 times of 6 is 9, isn't it? Yep. Which equals -1. So this is our lower boundary, -1, okay? Then our upper boundary is going to be 14 plus 9, which equals 23. Okay, so these are our outlier boundaries. So essentially, if I was just to draw the outlier boundaries right now, we know it's going to be from -1 to 23. Okay? Anything outside, actually I'm going to use a highlighter. Anything outside of this range is an outlier. But how do we represent outliers? Normally, if we were to draw this graph, we would do 0 is our smallest value. Our biggest value is 27. Okay, and then we have our median is 10. Then we have our lower quartile 8. Then we have our upper quartile 14. This is our normal box plot that we would draw for this data, okay? But I know from this, anything greater than 23 is going to be an outlier. So we do have an outlier here of 27. Anything less than -1 is an outlier. We don't have anything less than -1, so we don't have any lower outliers. But 23 is our outlier boundary for the top bit, and 27 is over that. So 27 is an outlier. Now what we would normally do is put a cross, but that doesn't look quite right, does it? Okay, because we want the outlier we want to show the whole representation of the data. So we could do one of two things. Okay, you cannot do them both. You do one or the other. When drawing your upper quartile, you can either use the second largest data value, and the smallest, which is 21. So that would come up to here. And then we'd have our 27 is our outlier, and it would look like this. Okay, this is one way we could do this. Okay, and so we've used our second, largest value. This 0 can stay as 0. Okay, because our lowest value is 0. Okay, we can't, but for here we can do that. Or what we can do is use the outlier boundary, which is 23. So, or you would still get points if you drew this box plot and used 23, which would be here. Personally, I would use 21. Why? Because there is no data value which is 23. The largest actual next data is 21, okay? So I would rub this out and I would use 21. Now there would be no point in changing this to -1 because we don't have any data values that go outside. If we don't have any data values, outliers in the lower bound, please use the smallest value as where you put it, okay? So have a look. For each one it is slightly different, so you will have different, a different box plot. Either one will do, but really think about it. The main things are, our box plot is now in our range of values, okay? Which do not include any outliers. And then our outlier, we've put a cross there to symbolise that. Okay, test your understanding again. 7 marks. And here are the answers. Please pause it and mark your work. Next lesson. Right. Page 40. Exercise 3C. I want you to do questions 3 and question 4. Then you're going to go to page 43, exercise 3D, page 2 and 3, questions 2 and question 3. Then you're going to go to page 49, 3F, and you're going to do questions 1 and question 4. Okay? So if I was to plot this like a normal bar graph, for example, between 15 and 20, the frequency is 15. Between 20 and 50, the frequency is 15. But this graph is not correct. Why is this graph not correct? So this represents 15 people, and this represents 15 people. But do they look the same size? Absolutely not. And this is why we have histograms, and we have to divide to get frequency density so that the proportion is still the same. Okay, if this area represents 15 people and this is 15 people, this should have the same area. Okay. This is an actual histogram, because what we have here is we have the same area is equal to the same frequency. Okay, so the area is equal to the frequency. So we know that we have to use frequency density, and we learnt this in GCSE. And what is frequency density? How do I calculate frequency density? Yeah, frequency divided by our class width. So what we're going to do is we know, if we have a look at the age group, and if we look at them spread evenly, okay, we have between 15 to 20, okay? So presumably, 15 to 20, we've got 15-year-old, 16, 17, 18, 19-year-old. We're technically saying there's like 3 of each one, if it was evenly spread, okay? But from 20 to 50, we've got 15. So there's only a gap of 10, isn't there? So, and that's going to be about 0.5, we're saying, roughly. Okay, so what we have to do is our frequency density divided by our class width. So we know our class width, if I do this in green, so we have 5, 10, and then we know our frequency density is frequency, which is 15. Oh, it's 30, sorry everyone. Um, 15 divided by 5 is 3, and then we're going to have 30 divided by, 15 divided by 30 is 0.5. Okay? So we should all be really happy on how we draw histograms. This is what we learned in GCSE, and to be honest with you, you're not actually going to have to draw them like we did in the GCSE. We're going to be looking at pulling information from them. So, bar charts versus histograms. First of all, bar charts are for discrete data. Okay, it's really important that you know these definitions. This is for discrete data, and it's the frequency is given by the height of the bars. Histograms is known for continuous data, And our frequency is given by the area of the bars, okay? So you can also see in bar charts we have gaps. In frequency density we do not have gaps, but sometimes they will say to you, why have you used a histogram, okay? Well, and this is because it's for continuous data, okay? Now, even though the GCSE definition is frequency is given by areas of the bars, we are going to look at a bit more in-depth definition. So here we have again our bar chart versus histograms. Now, Dr. Frost uses the triangle method. We don't use this. We just know that frequency density is frequency divided by class width, okay? So if we very quickly, we should be able to find out the frequency density or find out the missing frequency and write down for question 1. So if we have a look at question 1, we're going to do this as a class. So our class width is in fact 10, 5, 20 and 10. So our frequency density is frequency 40 divided by 10, we're going to have 4. Okay, we're going to have 6 divided by 5, 1.2. Okay, here we know frequency, something divided by 20 gave us 2.6. So 2.6 times 20, 52. And then again we know 1 divided by 10 gives us, something divided by 10 gave us 1. So the answer is 10. So everyone should be really happy figuring this out. Now, if we want to find the frequency given a bar chart, not a bar chart, a histogram, so we're going to do the area. So this is 15, by the way, and this is 45, just so you know. So, how do you find the area? Base times height. What's our base? What's between 10 and 15? 5 times 3? 15. Okay. What's between 15 and 30? 15 times our height is 2? 30. Here we have 10 and our height is 4. 40. Our base is 5 and our height is 5. 25. So this is everything that we did pretty much at GCSE. Okay. Now what we're going to move on to is we're going to move on to some skills, okay, and how, unlike GCSE, sometimes the area is not necessarily equal to the frequency. They're just not proportional, okay? They are just proportional. So sometimes the area doesn't equal the frequency. So this is something slightly new. So what we need to actually find is the scaling of the area, okay? So this is what we need to find. And if you remember direct and indirect proportion, we had our lovely K's, okay, because they are going to be in direct proportion. So here we go. Let's have a look at how we do this. So there were 60 runners in a 100-metre race. The following histogram represents their times. Determine the number of runners with times above 14 seconds. Okay? So, first of all, the total frequency is known. That's what we need. Total frequency is known. So to find the total area and hence the scaling, we know, what do we know? What is our total area? So total area equals 9 to 12 is 3, 5, so this is 15 units squared. 12 to 18, 6, and this is 1.5, so this is 9. So my total area is 15 plus 9, which is 24 units squared, or whatever we have right now. But actually, so this is where, even though we've got this proportion, how many do we have in total? 60. So we're saying 24 is proportional to 60 because we know our total area and our total frequency are different. Right. So so 60, our total frequency equals 24k because we've scaled it by something, haven't we? So to find k, we're going to do 60 divided by 24, which equals 2.5. Perfect. So to use this scaling, we know frequency equals k lots of our area. Okay? So in the question, it says, determine the number of runners with times above 14 seconds. So first of all, 14, roughly here. This is 14. We can work out the area of 14 upwards. 14 to 18 is 4. And we know it's up 1.5. So this means our area equals 6. 4 times 1.5 equals 6. I'm going to rewrite this. Our frequency equals 2.5 multiplied by our area. Now then, I know my area is 6. I can work that out. So therefore, my frequency equals 2.5 times my area, which is 6. So my frequency is, in fact, 15. So this means there are a total of 15 runners with time above 14 seconds. With times above 14 seconds. So you can see how we've used our proportion to scale what's going on. So what do we need? We either need total area or total frequency. We then need to figure out our k, and then we can use this scaling to answer different types of questions. So, test your understanding. This is from a 2012 paper. Have a look. So, a policeman records the speed of the traffic on a busy road with a 30-mile-per-hour speed limit. He records the speeds of a sample of 450 cars. Now, we should highlight this because this is our total frequency here. So we've been given the total frequency. So we know our total frequency is 450. The histogram in figure 2 represents this result. So we know what we have to do is calculate the number of cars that were exceeding the speed limit by at least 5 miles per hour in the sample. So what we actually have to do is we have to have a formula. Okay, we need the formula of frequency equals our scaling k multiplied by our area. So what do we need? We need frequency and we need our total area. So how do we work out our total area? Well, we find the area of each rectangle and find out what our area is. So there's a few ways you can do this. You can either A, find out, okay, so you can, if you want, go through and do each individual rectangle if you wanted. Okay, so I'm going to do 2 ways. So this one, I'm going to have 5 multiplied by 1.55. Okay, here I'm going to have 10 multiplied by 6. 5 multiplied by 4 point. Oh no, sorry everyone. That's not 5, I've read the scale wrong. That's just 5. That's going to be 4.5. Then we're going to have 5 multiplied by 1.5. And then lastly, we're going to have 5 multiplied by 3. So I can work that out and add them all up. I should get 112.5? Yeah. So our total area is 112.5. The other way you could do this is you could just find out, for example, that this has an area of 5. And then you can just count how many 5 by 5 squares you have. Okay? Completely up to you. Obviously, the most accurate way is to work out the area of each one. Right, so now we know our area. So we know that our frequency equals our K times our area. So 450 equals K times 112.5. So to find K, we're going to divide, and that means our K is actually equal to 4. So our formula is frequency equals 4 lots of our area. This is our formula. It now says, use this to find the number of cars travelling exceeding the speed limit by at least 5. So we want, the speed limit's 30, so we want greater than or equal to, no, at least. So we just want greater than 35. So we want these two. So we know this is 5 times 1.5 plus 5 times 3. Okay? 7.5 plus 15. 22.5 is our total area, isn't it? So our area for this is 22.5, where our frequency, well, yeah, we're saying greater than 35 miles per hour, aren't we? So now we're going to have frequency equals 22.5 multiplied by 4, which is going to give me 90. So this means, what does this 90 mean? 90 cars, okay, we're exceeding the speed limit. That's what that means. Okay, we have another question for you to test your understanding. This is part B of the question. When in doubt, go back to basics. How do we find the mean from a table? Because this is essentially, we've been given the graph, we don't know the table. Okay, but how would we find the mean from a table? We know this is between 10 and 15. That's not the way it goes. We know this is between 10 and 15. We then know we're going to have, 15 to 20. We know this is 20 to 30. This is what we'd have, wouldn't we? And then we'd have our frequency. Okay? And then how would we find our mean? What would we do? We'd do frequency multiplied by midpoint. We'd add them all up and divide them by the total frequency. So you can either A, create your own table so that you can do that. Or B, know that that's what you're doing, and for each one, you know the midpoint between 10 and 15, 12.5. Between 20 and 25, sorry, the answer is 25. Between 20 and 30, 25. 30 and 35, 32.5. 35 and 40, 37.5. 40 and 45, 42.5. So we would multiply our midpoint by our frequencies, wouldn't we? Now remember, if we go back to part A, we worked out that this was 5 times 1.5, so this was 3. Okay? No. What was the scale? Sorry, this is 7.5, isn't it? Okay, this is 7.5, but do you remember that didn't actually represent 7.5 people? We know for this scale at the minute, we know our frequency equals 4 times our area. Our area is 7.5. If we multiply that by 4, that means our total frequency is 30 for the first box. So we know we're going to have 12.5, our midpoint, by our total frequency, 30. Plus, we're going to find what all of them are, and then we're going to divide it by our total frequency of 450. So we know for this second one, we had 10 times 6, which was 60. But that doesn't represent the total frequency, does it? I need to do 60 multiplied by 4, because this is our formula. 60 times 4, 240. So I know for the second one, I'm going to do 240 times our midpoint, which is 25. Okay? This 240 represents the actual frequency. For the next one, what did we have? 5 multiplied by 2, 4, 5. Was this representing 25? Our area was 25 for this one?
No, it's
5 times 4.5. So our area for this one was 22.5. I'm now going to multiply that by 4. 90. So this is actually going to be 90 times 32.5 plus our area for the second one. We know this is 30 again. So we're going to have 30 times our midpoint, 37.5, plus our area for the last one is 60. Did we already times it by 4, yeah? Yep, so we're going to have 60 multiplied by our midpoint, which is 42.5. Divide that all by 450. And that is actually going to give us 28.8. So if we had a question finding out, the median or the quartiles, remember, even though we have the area, we do not have the true frequency. So this is why it's a step up from GCSE, because in the GCSEs, all of our areas were directly proportional to our frequencies. In A-level, they are directly proportional, but our scale is no longer 1. Whereas before, technically, our K would be 1, wouldn't it? Okay, whereas now it's not. So sometimes in the question, you'll see down the side here, they don't give you any values. You can just put any values you want until you find your K, and then you can find your total frequency. Estimate to 1 decimal place the value of the median speed of the cars in the sample. Now again, how would you do this? Just because we've been given a graph, don't, be thrown off. How would you do this if you had a table? You can always create your own table. Okay, then part D and E, we're going to come back to once we've done the whole of this chapter, because at the end of this is where we're looking at distributions and skewness. So we can come back and answer all these questions. Now, I actually find it easier to do linear interpolation by a graph, because I think it visually represents what we're trying to do, aren't we? So if we want to find the median, we know the total of the frequency is 450. So to find the median, we know it's going to be the 225th term position. Okay, it's the 225th person. Okay? Where is the 225th person? We know the first 30 are in here. We know up to between 30 and 270 is in here. So it's got to be in this bar here, hasn't it? So the 225th person is going to be somewhere in here. Where? We don't know yet. What I do know is this. So I know it's in this frequency. I know that I need to find my fraction. Okay? And my fraction from 30 plus what is 225? 190 divided by 240. This is going to give me, my proportion. My class width of the whole bar is 10, so I need to multiply that by 10 to know how far I'm going across, don't I? And then, 195, sorry everyone. Yeah, you're completely right. 195. And then I need to multiply it by 10 to see how far I've got to go across. Okay, because we're adding proportion, and then we've got to add it on to 20, and then we're going to know exactly where the median is. What do we get? 28 0.125. It then says estimate to 1 decimal place. So this is 28.1. So this is saying to us that 28.1 is where we're going to find the medium term. So if I was to, oops, I don't know what happened there. Wait there. There we go. So if I was to actually draw this as a straight line, I would go to 28.1, which is roughly here, okay? And then I'd get a ruler, because that's what we need. And I would draw a straight line. There we go. Wonky as that may be. This is where the median is, okay? So you've got to imagine, if this wasn't grouped data and you could write down, instead of putting it into groups, before it was put into groups, all of these 450 cars would have been written down as numbers. For example, we would have had, someone was going at 12 miles an hour. Someone was going at 10. Someone was going at 13. No one went between 15 and 20 for some strange reason. Okay? Then between 20 and 30, we're going to have 21, 23. But there's going to be 240 values in between 20 and 30. Okay? So imagine we had that really long list, and we need to find the median. Now, as you know, in practical mathematics, realistically, how often do you think you're going to find the median of a data set of 10? I know we do it in class and we find the median of a data set of 10, but realistically, that's not happening. When people use statistics, they are on, hundreds upon thousands. That's what the scale is. So all we're doing is, instead of sitting there and marking off, that, take away that, and then going to find the median, what we're doing is we know we can still find it using mathematics, and this is why mathematics is beautiful. It doesn't matter how many's in your data set. Using interpolation, if you find the proportion, you can find out exactly where the median is. An estimate for it anyway for this grouped data, because we don't know the exact values. As you know, in chapter 2, we have seen sometimes when we're given data, there are gaps. And what I mean by this is 2 and 3, there is a gap, okay? So, essentially, our class width, if you think about this, 1 to 2, it says round to the nearest kg, so you could either be 1 or 2. So what is our width, essentially? 2. 3 to 6, 3, 4, 5 or 6. So what is our width? 4. 7 to 9, 7, 8, 9, 3. Okay, so they've given us our frequency. So we know our frequency density is frequency divided by class width. So we're going to have 4 divided by 2. Then, for the second one, we know, 4 divided by 2, sorry. Oh, golly, 2. Okay, well, how do I find our frequency density? I'm going to do frequency divided by class width, 3 divided by 4, 0.75. Okay, then I don't know my last one, but actually, hold on. Now, you notice actually, with a graph, they draw it in between, just like, when we're trying to find the interpolation, we change it. So they draw it, they take away 0.5 from each. This is how you have to draw it. This is the scaling, essentially, that you have to draw. So here, we need to actually find, the frequency. Now, we know we can find the area. 3 times 1 is 3. And then, therefore, my frequency density is 3 divided by 3, which is 1. Okay, so there we go. We figured it out. Nice and simple. Any questions? Okay, test your understanding, please. So, So, the histogram in figure 1 shows the time to the nearest minute that a random sample of 100 motorists were delayed by roadworks on a stretch of motorway. Okay, so here we have between 4 to 6, okay, and the number of motorists is 6. 4, 5, 6. So what is our width essentially? 3. Okay, so we know our frequency density is frequency divided by class width. So 6 divided by 3 is 2. And this is how they've got the 2 here. You know, when they go up on the graph, it's up to 2. Okay, so 7, 8. How many is that? 2, thank you. So I think on here, it's 7, isn't it? Okay, so we know our frequency density is 7. So 7 times 2? 14. Oh, I'm going to put that in... Because remember, frequency density equals frequency divided by our class width. So if we want to find the frequency, we're going to do frequency density times class width, okay? Simple rearranging of equations. So then, 9. 1. Okay, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's 5. I think it's 1. Yeah, so 5 times 1 is 5. It's a very hard graph to read, actually. Okay, perfect. So this is filling in the graph. Oh, I didn't fill in the frequency densities. 9 divided by 3, 3. 45 divided by 3, 15. 21 divided by 1, 21. Okay. It then says, estimate the number of motorists who were delayed between 8.5 and 13.5 minutes by the roadworks. Now, 8.5 is here, and 13.5 is here. Okay? Now, no, this is 13.5. No, it's not. What is this? 12.5. This is 12.5. Okay, 13.5 is somewhere in there, isn't it? Okay, so first of all, what am I going to do? Now, I know, in this case, this is 100. And my motorists, do they add up to 100? Yeah, so in this case, my K is 1. This is directly proportional with a scaling of 1. Okay, so my area does equal my frequency. So I know I'm going to have to do 14 plus, no, it's not 14, sorry, 21, because that's the area of this bar here, the whole of it, plus the total area of here, which we know is our frequency, 45, plus, now, because I want the total. Now, I know between 13 to 15, this is actually in the graph as 12.5 to 15.5. 13.5 is here, okay? And if I think about the proportion, what's the difference between 12.5 to 15.5? 3. From 12.5 to 13.5 is 1. So I need a third of our frequency, which is 9. So plus a third of 9, which is in fact 3. So 21 plus 45 plus 3, 69. So it wants to estimate the number of road workers. So I need to add the area of this, which is 21, plus the area of this, which is 45, because this is motorists of 8.5 to 13.5. So far we've done 8.5 to 12.5, okay? But for the last one, I don't want the whole of it. I only want up to 13.5. Now, some people have just done 1 times the height, 1 times 3, whereas what I've done is I've looked at the proportion. Now, either way is right, but because we're doing linear interpolation and everything, we should be fairly confident that we can do this using proportion. Okay, so this is all we want, is the frequency of anyone, because it says 8.5 to 13.5. So I know that this is 8.5, and then 13.5 is in the middle of here. So I want all of this, and a third of this. Okay, so the next skill is the width and height on the diagram. So it says here, an exam favourite is to ask you what width and height you would draw the histogram. They won't ask you to draw it. Okay? So here is this typical question. The frequency table shows some running times. On a histogram, the bar for 0 to 4 seconds is drawn with a width of 6 and a height of 8. Find the width and the height of the bar for the second one. Okay? So this doesn't necessarily mean the area is completely in proportion with a value of k to the frequency. So step 1, find our formula. We know that frequency equals k times area. Okay? Now, they've told us the bar for 0 to 4 seconds is 6 and 8. So what's our area? 6 times 8, which is in fact 42. Okay?
Wait, no,
is it?
No, 48.
48. I was going to say that's 6 times 7. Right? Okay, so 48. So our frequency is 8, isn't it, for 0 to 4, because we've been given the table. So that means we have 8 equals k times 48. So 8 divided by 48, so our k is in fact a 6. Okay, so this is our fraction. Now, it says here our width is 6 centimetres. So that also means from 0 to 4, they're saying that that is 6 centimetres. Okay? So, first of all, let's focus on our width. Okay. So for our width, they're saying 0 to 4, which we know is a gap of 4, equals 6 centimetres. So what have we multiplied our class width by? Our class width times our scale factor equals 6. Okay, so 6 divided by 4 is 1.5. So we know our width for our 4 to 6 is going to be 2 multiplied by our scale factor, which is 3. So we know our width is going to be 3, okay? So this is going to be the width for the new one is 3. So W equals 3. Then the height of the bar for 4 to 6 seconds. Well, first of all, let's figure out the area, and then we've already got the width, and then we can divide it to find the height. So we know our area. So we know our frequency is, so frequency equals k, which is 1 over 6 times our area. We know the frequency is 9 equals 1 over 6 times our area. 9 times 6, 54 equals our area. Okay? So, therefore, our area equals width times height. So 54 equals 3 times our height. 54 divided by 3, 18. So our height equals 18. Now make sure we write units, okay? So maybe write again here. Therefore, width equals 3 centimetres, height equals 18 centimetres. Now, this is literally, it's just like a problem-solving question, really, isn't it? Okay, now again, this isn't the only way to do this. We have another way.
So
we know the difference is 4,
yeah,
and this equals 6.
And that equals 6. And then if you look at the other one, the difference is 2. Plus like 4 to 6, the difference is 2.
So the difference is 2.
And that's equal to x.
And this equals x.
So then you just cross multiply and then.
So 4x equals 12. No?
And then by
X equals 3.
x equals 3.
Perfect. So this is done by cross multiplying. Okay? And then how did you find the other one? So then the frequency density 8 over 4 equals 2.
Yeah, and then that 2 is equal to 8, which is the height.
And 2 equals 8.
And then for the other one, we have the difference is 2, so 9 over 2
And then 9 over 2
is equal to x.
equals 4.5. So 4.5 equals x.
And then
Cross multiply again. And x equals 18. And this is because you get 2x equals 8 times 4.5. Yeah, 36. Okay. Either way is correct. As long as you understand what's going on. Okay, essentially, this is the same way. And this is cross multiplication. I don't mind which way you use as long as you understand what's going on. Okay, test your understanding. So, the variable x was measured to the nearest whole number. 40 observations are given in the table below. A histogram was drawn and the bar representing the 10 to 15 class has a width of 2 centimetres and a height of 5 centimetres. For the 16 to 18 class, find the width and the height. Now remember, when we looked at data with gaps in, okay, when we drew the histogram, we still drew this between 15.5, okay, would be where our bar would be here, 15.5, oops. Okay, here would be 18.5, this would be 9.5, okay, so remember that. Now, again, personally how I would do it, so I know for 10 to 15, okay, I know that for 10 to 15, my width is in fact 6. So we're saying that 6 goes to 2, okay, so we're saying that 6 goes to 2. So what have I done to my class width? I've divided it by 3. So for the gap of 15.5 to 18.5, I have 3 goes to what? And I know to find that scale factor, I divide by 3. 3 divided by 3 equals 1 centimetre. Okay? Wait, I've written that wrong. This is supposed to be 1. Okay, and then for the height. Now, I know that 2 times 5 equals 10 centimetres. And that is my area, isn't it? Okay? Now, I know that 10 centimetres correlates to 15. So, what have I done? 10 to 15, I've multiplied by 1.5. Okay? Multiplied by 1.5. So, if I have a frequency of 9, what have I multiplied by 1.5 to get to 9? 9 divided by 1.5 is 6. Okay, so I know my new area is 6. Now, what do I know about, so 6 equals base times height, which is 1 times height, so my height is equal to 6 centimetres. Okay, so again, I've done this with complete logic, okay, and there's, this isn't a nice way, essentially. But again, there is a different way, okay? Now to find the width, okay, we know our width, 9.5 to 15.5, is 6. So this is the same as doing 6 equals 2 and 3 equals x, and then you cross multiply. So we're going to have 6x equals 6, so then x equals 1. Okay? That's the exact same as when we come to do the height. But with the height, we need to know a bit more. So with the height, did you work out, when you cross multiply, did you do the area first? So with the height, what do we know?
The height corresponds to the frequency density.
So the height, so when you do the height, you do frequency density.
Yeah.
Okay, so our height is 5 equals our frequency density. Is that 15 over 6? And our height for the second one is going to be 9 over 3. So I'm going to have 15 over 6x equals 15. So therefore x equals 6, okay? So again, either way, using your cross multiplication. Now, I know some of you have got formulas for this. I'd rather you not learn any formulas. You're going to have to learn so many formulas when we come to the end of stats, okay? You just need to understand why we're doing this. This is literally just proportion. It's practically ratio. It is ratio. Okay, something we haven't done. So in the GCSE, in the normal GCSE, they have something called a frequency polygon. Now, a frequency polygon is created by, and you just need to know this, okay? Frequency polygon is created by the midpoint of the height is where you connect. This is where we're going to put the points essentially, and you have to connect them with a ruler. This isn't a curve, okay? You have to connect them with a ruler. We're going to come back more to frequency polygons later, but when you see this term, this is what it means, okay? Sometimes they might give you a frequency polygon and then ask you to work out the height and width of the bar, okay? So it is easy to work out. But you need to know the definition. Okay, lucky for you everyone, it's that time of the lesson where you've got exercises to do. So, exercise 3A, question 4, 5, 6, 7. Exercise 3A, question 4, 5, 6, 7, page 34. So, we have a positive skew and a negative skew. Okay, now I want you to have a debate. Okay? Which tail is the direction likely to point? I want you to think the distribution of salaries in the UK, IQ, heights of people in the UK, and age of retirement. Right, so if you think about salaries in the UK or even in the UAE or anywhere, right? Sometimes what happens is we're going to have like loads of salaries which are around the same area, aren't you? And you're going to have some really high salaries. Now these high salaries are actually outliers which are going to make the mean increase, aren't they? But our median, where most of the people are, they're mainly going to be working class. Okay, so it is going to be more of a positive skew because we're going to have the outliers, but the reason why it's positive is because the mean is greater than the median. So even though if you think about it, we're going to have some people here, the majority of people are going to be here. Yeah, and then you're going to have some low people, but you are going to have people that are going to keep going. Okay, it's going to be a positive skew. Okay, IQ, measuring someone's intelligence. Okay, this is actually going to have no skew. okay, because it's going to be symmetrical. Okay, this is what we call a symmetrical distribution, and this is because the mean equals the median. I spelled median wrong earlier, no one told me. Fool, I tell you. Right then, median. Heights of people in the UK. Okay, there's going to be no skew here. Why? Because you're going to have so many population at this height, so many population at this height. But what we're going to have is no one is going to exceed a certain height, are they? Realistically, no one is going to be over 7 foot. Okay? So, the mean, again, is going to equal the median because the majority of people are adults. Okay? And they're roughly, what do we reckon? When you get to about 18, you're roughly fully grown? And then from 18 to what? The age of, let's say, 70, you probably stay roughly the same height. I know sometimes older people shrink. I'm not sure why yet. Okay, but this is not going to have any skew. Then, age of retirement. What age do people retire? Now we're going to find this is going to give us negative because we're not going to have many people young, are we? But then, some people retire at 50, 60, 65. Okay? This is going to give us a negative skew. And this is because the mean is less than the median. Here we have a typical exam question made up by Dr. Frost. It's not typical at all, but I am going to give you 2 marks for it. So, describe the skewness of the marks of the students, given a reason for your answer. The mean is 55.48 and the median is 56. Is this a negative, a positive, or no skew? And it's negative. Why is this negative? And it is because the mean is less than the median. Okay? 55.48 is less than 56. Okay, so here we go. Have a look at these quartiles and let me know the skews of these. Okay, so here we have it. On here, the data is more spread out towards the positive direction. So we know this is positive skew. On the second one, it's more to the right, which is negative skew. And here we can see that they're equal. So this is going to be no skew. Now also, another way to work this out, if you're not sure, is if you did quartile 3 minus quartile 2, if this is bigger than quartile 2 minus quartile 1, then you know it's positive. So if this is bigger, okay, we know this is positive. But on this side, if this section is bigger than this, we know it's negative. If these 2 sections are the same, we know there is no skew. So, here we go. On another occasion, the teacher calculated the quartiles for the times taken by the students to complete a different Sudoku. Yeah, people do play Sudoku. And this is what they found. Quartile 1 is 8.5, quartile 2 is 13, and quartile 3 is 21. Describe, given a reason, the skewness of the times on this occasion. Give you a clue with these types of questions. Instead of trying to remember a formula, draw this as a box. If you think you have 8.5 here, 21 here, where is 13 going to be? It's going to be closer. Here. So this is actually 4.5, and then 13 to 21 is 8. 8 is greater than 4.5. Therefore, this is going to give me a positive skew. Now, the reason you will have to say quartile 3 minus quartile 2 is greater than quartile 2 minus quartile 1. But we can see by drawing the box that you don't have to remember the formula. You can get this from drawing that middle section of the box plot. Okay? Remember, if the gap is smaller on the left-hand side, this means we have a more positive skew. Because remember, this 13 represents the median. This means the median of the data is more towards the left. If the median of the data is more towards the left, it's positive. If the median of the data is more towards the right, negative. If it's exactly in the middle, no. Okay, here we go. Test your understanding. You have 3 questions. You need to make a comment on the skewness and why this is true. Here we have the mean 5 is greater than 4. So the mean is greater than the median. Therefore, we're going to have a positive skew. For the second one, again, what am I going to do? I am going to draw the box. 3, 6, 5. I already can see that this is in fact a negative skew. Okay, and instead of remembering a formula, I know that this is quartile 3 minus quartile 2 is less than quartile 2 minus quartile 1. I can do that. I don't have to remember that. I can do it from drawing the box. Now, the last one. 5.72 is greater than 5.71. But, how close is it? Okay, this is little to no positive skew. Okay, so because 5.72 is roughly 5.721. If you were to round that to 1 decimal place, it's 5.7, it's 5.7. Just watch out for that. You just gotta, it is positive, but it's very little, isn't it? You think the bigger the gap, the bigger the skew, really. The more, you know. So, one measure of skew can be calculated using this following formula. This is given to you in the exam. Okay, it's not in the formula sheet, but if they require you to use this in a question, they will give you it in the question. Okay? So, what we have to do is figure this out. So we know the mean of these salaries is not a lot. Add them all up and divide it by 1, 2, 3, 4, 5. So we're going to get 23.50. The median, the middle number, is 4. Standard deviation. Remember? So standard deviation is the mean of the squares minus the square of the mean. Okay, we're going to put this into our calculator, or if we want, we could use our calculator to put these in, couldn't we? And we're going to get 38.28. So then, the skew. 3 lots of the mean, 23.50, minus the median, divided by standard deviation. This is going to give me 1.53. Now this is a positive number. So this means we have a positive skew. Because 1.53 is greater than 0, we have a positive skew. If we had negative 1.53, negative skew. And if it equals 0, no skew. Okay, so now for the rest of the lesson, you're just going to go through the exercises, okay? Exercise 1, if you're feeling meh. Okay, take a second to mark your work. Go straight to question 3 if you're ready to actually do an exam question and then discuss the skewness. Here are the answers for the next exam question. And go to question 4 to also do an exam question and discuss skewness. Here are the final answers. Okay, well done. This is Stats Chapter 3. Over and out.